we're accelerating today, doing this from the actual from the car. Anyway, I'm just gonna try to get some thinking straight. Okay, I'm really just trying to think about this. I'm not trying to actually code today, although I might test for things. But again, let's remember. So I mean, yeah, it's the damn thing with the what I tried last time was to even define the objective function for just around W1 and not W2, right? But it's exactly the same problem, which again, like first principles, right? It's a function. It's a function whose derivative of the softmax function. It's a function whose derivative. I'm not so sure I fully understand, right? Derivative of the softmax function. Derivative. The Jacobi matrix of the softmax function, which contains all the partial derivatives, is given by these. It's super loud outside, so that's gonna be a nasty video, I guess. I'm sorry, but that's the way it is. That's the way it is. Can I see that? No, that's just like some weird latex stuff. I cannot increase my volume. I hope it's loud enough and they're not getting too much noise. The derivative. Okay, is that so? I mean, this is for sure. The derivative is like this. This means, well, okay, kind of makes sense, right? It would make sense. I mean, this I could try, right? Because we can plot this. Objective W1, we can actually plot this, right? Okay, but here, as matrices, I mean, so I would need to kind of get this whole thing generated. Why would it make sense though that most of it from a derivative standpoint is like that? Why would this make sense? And wait, this is just very where is this from? ResearchGate? Is that so? Do I have access to the full text? The softmax activation function and its derivative. Yeah, well, I guess that kind of it depends on what you're using as x. right? Hmm. But okay, I guess what that's telling you is that really, really the peak is here, because that's where you have already the minimum, right? And then, but I don't know that that second part here makes sense. Here, this sort of makes sense, right? Because the higher the probability, here the lower the derivative, right? Mm, yeah, well, that doesn't necessarily make sense either. That doesn't necessarily make sense either. Hmm. But that would explain if this is something that is very sort of narrow, right? Then a lot of values are just going to be zero, right? Because this is a very narrow sort of interval, right? Here, this stuff. Like many values, like whatever is like below, like after -4 and +4, it's just going to always be zero. So I guess the same problem is here with matrices, right? So yeah, but how to solve these? I mean, that should just be anyway, not exactly like this, but it should just match how the distribution looks like, right? I'm having problems interpreting this because the softmax is quite of a funny function, right? Because it's like it's a function that depends on give me a second, guys. It's a function that depends on its own input distribution. Actually, what is the derivative of that? Like, it's a good question. What is the derivative of the average function? Like the function called average. I've never asked myself. That's actually a funny thing, right? That's quite a so average x and never thought about these like that. No. So the function average. Can you do a derivative of the function average of x? Can you do something like how is that even defined, right? That's probably what we should be asking ourselves first. Where was I here? Let's ask the AI. Can you do? How do you even define that, right? That's the calculate the average mean of the elements and least. Which is a mathematical function that finds the rate at which a function is changing at any point. It's like finding the slope of the function at a given point. Can you differentiate which function? Is a continuous variable rather than discrete one? We can think of about taking the derivative. Now input x is a continuous variable rather than a discrete least. So the derivative of the average function interpreted as a continuous independent variable is 1 if each element of x is just x. Okay. It doesn't quite apply, but that's what I like. If the concept of differentiation doesn't quite apply to the average of x, then why would it apply to softmax? So the derivative is simply 1. Okay. There's no standard function called average x. The constant of an average value function is typically defined using an integral, not a derivative. Blah, 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 blah. Because the definition of softmax, then, that would just be kind of, would fall under the same kind of question, right? It's something that just depends on that. Fuck, man. How do you even do that? Can you give me code? So give me code that uses AutoGrad. What's the AutoGrad? What would it actually tell me when I do this? Oh, what? No. No. Okay. That should just be new file. What if we just like do return NP average of x? Okay. Shell basically Python. Does it do anything? So NumPy, does NumPy have an average? Is it really called like this? Stop. Okay, so is it really like that? What? Wait. AutoGrad? AutoGrad doesn't. What? Okay, just Python codes to calculate an average of an array. Like, oh, just like that. It's simple, just like this. Without don't like without. I mean, just add the whole thing and divide by, right? The sum, yeah. Now it will tell me that it doesn't implement that either. What? What is it doing? X and Y must have the same first dimension. I don't get it. But has shapes 400 and 1. Okay, yeah, okay, that is because here it's the wrong thing to do because it's basically mapping. It's mapping from an array to a number, whereas softmax maps from an array to an array. That's the wrong thing to do. Okay, it's fine. Yeah, it's maybe not. It's not the same type of question. I get that, but still, how can the softmax derivative make sense at all? That's what I don't understand, right? That's what I just don't get. I don't get what the intuition would be there, and how to deal with these, right? It's the softmax activation function. So why is the derivative of the softmax function killing my gradient descent process? Essentially, I don't get the loss to move. You know what I mean? Fine, you say that every time, but I don't really propagate it backwards on the output layer. If these gradients become very small, a problem common in deep networks, the updates to the weights during the gradient descent is next one is known as the vanishing gradient problem. Flat regions, if the Lockheed's input scores to the max are large and extreme, softmax outputs near 0 and 1 can make. That is probably what's happening, right? Because I guess if we assume that's true, probably the closer this is to something like the narrower this spike is, right? And so this makes basically the loss. I think that's what it is, but I'd like to understand why is this something to be expected, right? If the logits are large and extreme, then the softmax outputs are near 0 or 1 can make the derivative is extremely small, causing the gradients to vanish. I think that's the key. But then what is the point? Regularization, gradient clipping. That is what's probably happening, right? The probabilities are just kind of like too high. If I would force this logits to be two things that bother me. I don't grasp the concept of the derivative intuitively of the softmax function, and yeah, basically, right? Yeah, basically, I'm still. I'd like to understand that function intuitively, really. the derivative of that function. The softmax, it's okay. You can't easily plot it. The plot depends a lot on the plot. The plot. It's just the plot. It just makes no sense. How can you plot the softmax function? You can't, right? Because the softmax function takes you from an array to an array. So essentially, you can't just plot this thing. You just can't plot this thing. The input of the softmax function is basically a map from an array to an array. So I guess the thing is the rate of change here, right? So I think the concept, if it plots one thing to another, and what we know that it's doing is it's just basically kind of doing a bit of an average thing, right? Where it's normalizing everything between 0 and 1, but kind of like respecting the relative distances, right? Now, this means essentially that you get from this, you get like zeros and ones and whatnot, right? Now, the derivative of this function, I guess maybe it can be seen as the rate of change, as in like, if you imagine how different, yeah, but there's no, like, how do you define the, how do you define the domain, like the input space of that function, right? Because essentially it's like, what is it? It's I guess all the different probability distributions. No, how do you even define these for this to make sense? The rate of change of what? Well, I guess no, there's just something that is just off. I'm looking at the derivative of a function that has softmax in it, right? And it's a derivative with respect to something. This just has the softmax in it. The softmax, if your logits are very sharp, then the derivative is going to be very small. Why? I guess because, yes, okay, I think I know. Because then it doesn't matter how you change the input, the rate of change of that softmax is going to be still pretty much the softmax to calculate. Okay, if I think of, basically, if your logits have a very spiky distribution, essentially it means that yeah, so no matter, if what's happening is that no matter what input you're doing, you're always getting the same kind of distribution. There's not going to be a lot of change, right? I think you have to see it like this. It's like if what you're getting is no matter what you're doing, so if no matter what like input values you're putting, your logits are always because you've run through all the stuff, right? So you've run through all the training samples. You end up with a certain function that essentially what's happening is, if you think about the landscape of this, and then you think about the domain as like all the possible things that it's seen in the past, that it's been trained on, there's no variability, because essentially what it's just saying is that no, this makes no sense. What am I saying? That's weird, right? Because the softmax really just kind of you have a softmax. What is a softmax? You have a softmax. Wait a second. So you have a loss function. This loss function has a softmax in there. This means this loss essentially the loss. I'm getting lost in just reasoning. You know what I mean? I'm just getting lost in the essential reasoning of like, if I just have a loss function, this loss function tells me what is the loss function telling me? The loss function is telling me how far off the expected value I am, right? So you want to minimize that. Now this how far off, the problem is that the softmax function gives you probabilities, right? Because essentially how far off are you, but maybe just is not needed, because how far off are you can just be done at the logits level, right? Why do you even need the softmax function? You don't really care. The softmax function is just to make it nice, like to make it easy to just like pick something. But essentially, the logits is what matters. Do you really need to include the softmax in? Do you really need to include the softmax at all? Because it just makes no sense. The loss function is how something differs from your ideal probability distribution. Yeah, okay. But of course you're comparing probabilities with probabilities, so this has to have the softmax. So essentially, how you do these? If your softmax function if the way that this is set up from a logits perspective, if no matter what, how would you even reason about these? How? I don't know, man. I feel I'm almost there. It's not crystallizing in my head. Man.